What does it mean for someone or something to learn? Let me ask you that question before we do anything. The very concept of this is easy to describe, but it's hard to quantify. In machine learning and AI, we explore this notion because the fundamental basis that every AI you see today sits on is that one question. What is learning? Before we dive into what machine learning really is, I want to take a look at something even more fundamental, the data that supports it. In order to learn, you need content. That's the most important step here. You need something to learn, nothing more to it. And in machine learning terms, we call this notion data, or something that holds information. When you learn, you gain information from that data. Let's call our learning material or data set D. Okay, now where does this data come from? The answer is actually a bit philosophical, and it comes from nature, which we call the data generating process, or DGP for short, which is the underlying unknown mechanism that produces our data. We don't know what it is or how it works. All we know is that it exists. And in this light, we can see any data set as a sample or proxy from the DGP. If that didn't make too much sense to you, picture the DGP as like a giant ocean, a massive ocean where you, who are a scientist, you want to measure the saltiness of the ocean, how much salt is in there. The problem is that the ocean is way too big and way too unpredictable, so you can't access it all. That saltiness of the entire ocean, or data generating process, is unknown to you. So what you do instead is you grab a bucket and then scoop a sample of the water in the ocean, just a small bit, and you hope that this sample is accurate enough to represent the entire ocean, the sample that represents the entire population. Recall that our goal is to understand the ocean, not the bucket. Our bucket is just a proxy, a shortcut in order to approximate what our true goal. To translate that, in machine learning, we train a model on that data set or the bucket and hope that it can approximate or perform well on the DGP. That's the core idea of data. Okay, but what if your data is biased? What if you got unlucky and your bucket of water just so happened to contain the water that had the highest concentration of salt? Even more fundamentally, what if your data is not representative of what you want to generalize to, or the ocean? In the real world, everything is unpredictable. No dataset is ever perfect. There could be bias, there could be noise. And because of this, there is always that risk that we can get led astray, making us perform poor predictions, make assumptions, or just memorize the data. It's a problem that's still not solved in machine learning. And just to give a brief overview on it, we call it overfitting. The opposite, which is if the dataset is too complex that we can't learn anything meaningful, that's underfitting, and it's a trade-off. We need the dataset to be meaningful, but not overly complex. Underfitting and overfitting are two of hundreds of diverse problems within data, but they all point to the same thing. Nature is unpredictable, and yet we want to predict it. Machine learning tackles three fundamental questions, and in three entirely different levels. First, how do we create chatgpt? The second is how can we use what we know to predict what we don't know? And the third is what is learning and why does it work? So we have the data, and to analyze it, we need an algorithm or a way to learn the data. We want to discover a pattern in the data that is consistent with the pattern in the DGP. Specifically, we are given an input and need to find a pattern to produce an output or a prediction that we'll make. An algorithm is thus a mapping between an input and an output. It's a function that maps something from the input space to something from the output to the output space. In machine learning, we want to find this algorithm that can fit it as accurately as possible and generalize as strongly as possible to the real world. Okay, so we have our data set, our material that our AI learns on. We also have our function or algorithm whose goal is to model this data set and learn from it as good as possible. But look at that line again, as good as possible. How do we concretely define how good the function is? How do we know how accurate it is? For an AI to improve and learn, it needs feedback. So we need a metric. And to do that, we need something called the loss function. The loss function measures how wrong or off the model is to the true answer. Let's say the true answer is 5, and we predict 3. The loss is thus 5 minus 3 equals 2. It's not bad, but it could be better. If the model predicts 4, then the loss would be 1. That's better. We can see that machine learning is about trying to make this loss or measure of wrongness smaller. The model's goal is to find or make a prediction that is accurate enough or small enough and close to the true answer. We want to minimize this loss, which is why we call it empirical risk minimization. As you can see in the formula, we want to take the average loss across all samples in the dataset, where n denotes the number of samples. So now we have a rock-solid formula for computing how wrong we are, or how accurate we are on our sample. But one question is, why can't we just measure the wrongness on the DGP itself? Why can't we just look at our predictions and say how different it is from the actual answer of the DGP? The answer is we can't. Because remember that we can't actually access this unknown nature force. We only know it exists and we want to understand it. This is impossible. But let's stop for a minute and let's be theoretical. Assume that there's a hypothetical scenario where we can miraculously, suddenly be able to access the DGP. We have a God's-eye view, or the error we would see if we knew everything about the universe. Then we use the formula below, expected risk. It's the one on the DGP itself, not necessarily on the data. Of course, we seek to minimize the expected risk, but the only one we can have access to is empirical risk, which means we can only rely on hope. We hope that we minimize the expected risk by minimizing the empirical risk directly. However, a profound concept is about the gap between them, which is called the generalization gap, and we'll call this, cover this later. The function space is the function space is the space containing all possible models to fit for the data set. We want to find the best possible function in the set of all possible functions in this function space. This reveals a deeper insight. We can also see machine learning as searching that function space, searching the set of all possible functions to find the best one for our data set. We can also see it as constraining the function space until we find the best possible solution. However, in practice, we almost never find the best possible function in complex tasks involving non-convex optimization. But it's nice to think of machine learning that way. All that we need to know is that somewhere in this space, consisting of all possible functions, there exists the best possible or optimal model. We just need to find it. The definition of ML or machine learning is described in this slide. Previously, we said that the goal of machine learning is to train a model on our dataset or bucket and hope that it is accurate to the real world or the DGP, or in our analogy, the ocean. We discussed how the DGP is unpredictable and how the dataset can be a bad or biased proxy for understanding this. Now we know two more concepts: empirical risk and expected risk. One measures how accurate we are on the dataset, and the other measures how theoretically accurate we would be if we just so happened to know everything about the universe. See the connection? We can see that the definition of ML is machine learning is the study of minimizing the empirical risk, but we also hope to minimize the expected risk. The expected risk is more important to us because it's how the model will perform in the real world when exposed to the actual ocean. But the empirical risk is the only one we can actually use. We are taking what we know and applying it to the unknown. We are using what we know and predicting what we don't know. In summary, let's start with the analogy, the scenario with the ocean and the bucket. You're a scientist and you want to know the saltiness of the whole ocean, but it's way too large, unpredictable, and impossible to understand. Instead, you have a shortcut. You take a sample of the water, a bucket, and hope that it represents the ocean well enough to generalize. But sometimes you get unlucky and the bucket isn't a good sample. It can be noisy, biased, or poor quality. No matter what bucket of water you pick, they will never perfectly represent the ocean. In machine learning, we want to understand the information that we have from the bucket and predict what we don't know, the saltiness of the entire ocean. To do that, we need an algorithm, which is a function that makes a prediction when given information. We evaluate how good this function is using empirical risk, which is the average of wrongness across all data points. But we hope to compute and minimize the expected risk, which is the theoretical loss if we miraculously knew everything, but we don't have access to that. We want to find the best possible model or algorithm within our limits that can help us with this task. In learning theory, we define these two notions: what you know and what you don't know. Machine learning bridges these two notions and asks the fundamental question: how can you use what you know to predict what you don't know? In the next episode, I will be talking about the historical arc of AI, not the theory. It's about the imitation game, the original thing that started artificial intelligence. The Dartmouth workshop, which is the workshop in which the term was actually coined. And symbolic AI, which was the original form of AI. It was prominent in the 1900s. And the Chinese room argument, which argues against the imitation game and proves why AI might be not intelligent as we think it is. We'll also talk about the AI winters and the Lighthill report, and how for years researchers gave up on AI because they believed that there was no success in the field. Syntax and semantics, memorization and generalization, connectionist AI and deep learning, which is very modern right now, and the very recent phenomenon researched called grokking. Thank you so much for listening.